Section 3.11, we're looking at some properties of logarithms. So there are the three main properties of logarithm: the product property, the quotient property, and the power property. And then this little ancillary thing of the change of base formula that's hardly ever used anymore. But the first three properties we're going to need. Okay, so we're starting off with this example here where they've got some data, and I went ahead and plotted it into decimals while I was getting this set up. And that's what it looks like. Does the data seem reasonable? And so this is about dropping balls like we did in the last section. And so it does seem reasonable, hopefully, that we should be increasing by a decreasing amount because the ball is going to rebound at a slower and slower pace until it stops from bouncing. Okay, so we'll say yes because the data should increase at a decreasing rate. Okay, increase at a decreasing rate. There we go. Okay, now instead of doing a regression to find the equation here, they've given me a model to test out. It's written in number, I guess I should read number 3. Do you believe the data can be modeled by a logarithmic function? Mimic what we said below. Yes, because it's increasing at a decreasing rate. Okay, then they gave us this model down here. T equals 26.75 times the log of n. And that model does a fairly good job of fitting this data. Now, they didn't use regression here because, first of all, they did not want us to have the a plus the b at the end. They wanted just the b in this case because they're trying to show us the property of logs. Now, normally, the model type might be a plus b natural log of x. And again, we've moved away from natural log into common log just so they can demonstrate the property of logs. So we're just trying to say, did this model do a good job? Sure. Is it the best fit? Oh, I don't know, but it's pretty darn close. And again, the base of the log is flexible. It's irrelevant in this case. So it can be whatever it wants. It's just the parameters would change based on what it was. So we want to use this one here because it's going to help us demonstrate the properties and show that they are working. So I'm going to make this a function, just t of n, so I can type in another table with my function t of the x2s. And we're supposed to plug in 2, 5, and 10 to our function. Okay, so in 2, I get 8.05. With 5, I get 18.7. And with 10, I get 34.8. Okay. How are the t-values for n equals 2 and n equals 5 related to the t-value for n equals 10? Well, 2 times 5 is equal to 10, so multiplication. Okay, how are the results, the outputs? Using the results from part B, how could we determine the total rebound distance after 10 bounces? Well, I could, I don't know, I already have the 2 and the 5. But do I multiply? I multiply the inputs, but do I multiply the outputs or do I add the outputs? Let's experiment and find out. So I don't have 10. Was I supposed to have 10? Oh, I was. Was I? I was. Oh no. I was supposed to have 10, not 20. That'll make a lot more sense. Let's change this for 10 to 26.75. Oh, okay. So now I want to know how these two values are related to this one. So if I take 8 plus 18, that's It's 26, and 0.05 plus 0.7 is 0.75. So they're added. Okay. There we go. So if we take t of 2 plus t of 5, that is 8.05 plus 18.7, that adds up to 26.75. That adds up to t of 10. Okay, so that's our sum. And that's what they're demonstrating down here as well. And so this illustrates the product property of logarithms. That if you have the logarithm of a product, it's equal to the sum of the logarithms of the two components of the product. This isn't the first time that a product has turned to a sum or vice versa. The other property that comes to mind is if you had, say, x to the third times x to the fifth, that would be x to the eighth, right? Because x to the n times x to the m is x to the n plus m. So in exponents, exponentials, if you're going to multiply, you're going to add the powers. And so in logarithms, if you're going to multiply, you're going to add the logarithms. And that's because the answer to the logarithm is the power, right? So you're going to be adding those. The similarity between these two properties is because, again, they're inverses. So they are doing the same thing or opposite thing of each other. So the product is inside, the sum is outside, versus the product is outside, the sum is inside. That's the opposite part. Okay, so we're going to apply this property, just keeping in mind that they're related to the same exponential property. All right, so I can write log base b of 7 times log base 3 of 13 as log base b of 7 plus log base b of 13, separating into two logarithms. So we're using the property of logarithms to rewrite as a sum of two different logarithms. Okay, I'm going to do the same for the next one. There are three things in this product now, x, y, and z. So I'm going to separate into three pieces. So the log base 3 of x plus the log base 3 of y plus the log base 3 of z. Okay. And then log of 15. Well, that's just one number. However, I know that 15 is 3 times 5. So this is the same thing as the log of 3 times 5. And then I can separate that into the log of 3 plus the log of 5. That's a common log, so the base is 10. I don't have to write the little 10 because of the base. This next one's a natural log, so the base is e. It's not written there. And again, there's three things in this product. This one's going to be the natural log of 3 plus the natural log of x plus the natural log of y, separating all three of those things. Okay, then we're going to go in reverse. We have the sum of logarithms, so we're going to apply the product property to shrink that back into a product. The natural log of a plus the natural log of b plus the natural log of c, that's going to be the natural log of abc. A times b times c. And then the log base 4 of 3 plus the log base 4 of 9 is going to be the log base 4 of 3 times 9. And since I know what 3 times 9 is, I can go back and finish simplifying the inside. This is going to be the log base 4 of 27. So sometimes it's convenient to separate them if you're trying to isolate a variable. Sometimes it's more convenient to pull them together if we're trying to simplify a number. All right, so now we're going to look at the logarithm of a quotient from that same table. And just kind of noting that if I did, let's see, the log of 2, which is 5 divided by 10, I could take the difference of the log of 10 minus the log of 5 to get the log of 2. So 26.75 minus 18.7 is 8.05. Okay, so this suggests another property which is demonstrated further below. So we're going to look at it again. This suggests the property that if you have a quotient, you're going to turn that quotient into the subtraction. So we're just going to demonstrate that that's true. Okay, so I want two functions. One of them is the log of x over 4, and I want the other one to be the log of, oops, gotta do g of x, equals the log of x minus the log of 4. And so we're going to make a table with inputs 1, 5, 10, 23. Okay. And I'm going to do f of x1 and g of x1. And what we want to show here is that the outputs are identical for these two functions. So each of these functions is doing the same thing, just in a different way, but these two functions are equivalent, are equal to each other. So you can see that from the outputs that you're getting the same exact output either way. So if you're plugging in 1 to either of these functions, you're getting negative 0.60. If you're plugging in 5, you're getting 0.097. You're plugging in 10, you're getting 0.398. And if you're plugging in 23, you're getting 0.760. Okay. Is the expression log of x over 4 equivalent to log of x minus log of 4? Yes, because the outputs are the same for any input. Okay, outputs are the same for any input. Sketch the two graphs. Okay. There are the two graphs. If you unclick one or the other, you can see that they're on top of each other, so you're only going to see one graph. The graphs are the same. The graphs are identical. And what does that suggest? It suggests equivalent expressions. So into our properties box, this suggests that the log base b of capital A over capital B, that's going to be equal to the log base b of A minus the log base b of capital B. So a multiplication turns into an addition, and a quotient, a division, turns into a subtraction. That's very similar to what you remember from exponents. So if you would have had x to the 4th over x to the 3rd, that would be x to the 1st, or whatever it was, x to the n over x to the m is x to the n minus m. So we subtract powers when we're dividing with exponents. So if we are dividing inside of a logarithm, we're going to subtract the logarithms. So analogous properties there. So now we get to do some separating of our logarithms in number 9. Log base 6 of 17 over 3. That's the same thing as the log base 6 of 17 minus the log base 6 of 3. Log base x over 20, or natural log of x over 23 is the natural log of x minus the natural log of 23. Log base 3 of 2x over y, that's the log base 3 of 2x minus the log base 3 of y. But I have a product right here, so we're going to separate that product into a sum. So this is going to be the log base 3 of 2 plus the log base 3 of x. minus the log base 3 of y. So separating my product using the product property of logarithms in addition to the quotient using the quotient property of logarithms. And our last one, there's a quotient here. So we're going to separate this into the log of 3 minus the log of 2z. But there's a product there, so we're going to separate that again into the log of 3 minus the quantity log of 2 plus log of z. This entire thing is negative, so this negative needs to distribute into both parts. So I would finish simplifying that as log of 3. That 3 looked a little small. Let me make it bigger. It's not the base. Log of 3 minus log of 2 minus log of z squished in there in the edge. Okay. So these two both ended up negative because when I distributed this negative, and they were both in the denominator. So if they're in the denominator, their exponent, which is their logarithm, should have been negative, right? So they have a negative coefficient to their logarithm because they're both in the denominator. Over here, only one thing in the denominator, only one thing negative. Keep that in mind when we go down to number 10 when we pull things back together. Okay. You might want to reorder these or just group the two positive ones together because the two positive ones are going to come up into the top. So I'm going to do those two first. This is going to be log xz minus the log of 4. And then you can pull your quotient together. Log xz over 4. And then these two that both have a negative, they didn't distribute it for us, which is fine. I'll factor back out. They both have a negative, so those are going to come together in the bottom. Or I would have here log x minus log 4z. And so this one comes together as log x over 4z. So the parentheses here in this addition inside the parentheses with a negative means that this one is also going to have the negative associated with it, so that z is going to be in the bottom. Without the parentheses, this z is positive like the x, so it's going to go up, combine with that one, go up in the top. Negative signs signify that it should be in the bottom of our log. All right, so graph a pair of things here. Let's get a clean graph. Y equals the log of x plus the log of 4, and y equals the log of x plus 4. Okay, these are not the same, so they're not identical. So how do these graphs compare? They are not the same. And so what does that suggest about the relationship between those? They're not equal or not equivalent. Okay, so the log of a plus b is not equivalent to the log of a plus b. The log of a plus the log of b. The log of a times b, that's your equivalency. Log of a times b is equal to the log of a plus the log of b. Not the same thing as the log of a plus b in parentheses like that. Can't separate the addition into the addition of logs. What I do separate is the product into the addition of logs. Okay, logarithm of the power, the third property. Okay, so I've got two formulas to look at and compare. So I better make these functions. I've got the log of x to the third and 3 log of x. We're going to plug in 2 and 7 and 15. Little f, hold on. Okay, so as you probably saw when those graphs popped up, they were popping up right on top of each other. Those functions are equivalent. So the first one, when I plug in 2, I get 0.903. Second one, same thing, 0.903. When I plug in 7, 2.535. and 2.535. And when I plug in 15, 3.528, and 3.528. Exactly the same. Sketch the graphs. The graphs appear to be equivalent. Okay, so these things are equivalent. Okay, and so that gives us to our third property. So log of x to the third is the same thing as 3 times the log of x. So if you have the log base log base b of a to the p, that power p can be multiplied by the log base b of a. The property that this one is similar to is the power on a power property for exponents. If you have x to the fourth to the third, that's x to the 12th, or x to the n to the m is x to the n times m. So if you have power on a power, you multiply the two powers together. So since a logarithm is already a power, if you have a power on top of your power, you multiply the two powers. Remembering that the answer to a logarithm is a power. So this power is multiplied by the other power. It's a little harder to see that this is the same thing as our exponent rule, but it is. It comes from the same place. The power p is multiplied by the power, the exponent, that is the answer to the logarithm, according to the same property. Okay, so let's use this property over here for number 13. For this property, I like to circle my power and just like I'm pulling it down, right? My power comes down. So this thing is the same thing as 1/2 times the log base 3 of x. Okay, power and a power, that power comes down. So this is 3 times the log base 5 of x. Power comes down. This one's 2 times the natural log of t. Now on this one, I have to rewrite. They gave me a hint here. I don't see the power when I see the cube root of 50, but I can rewrite that as 50 to the 1/3 power, because that's what a cube root would be, in exponent notation. Then I can take my power down. So this is 1/3 times the log of 50. Oh boy, there's a lot of stuff going on in this one. I'm going to have to separate this into addition and subtraction before I can pull powers. So we're going to write this as the log base 5 of x squared. I don't have a lot of space here, so I'm going to go ahead and take the 2 on top, which are multiplied, and separate and add them. So plus the log base 5 of y to the third. Then our division turns into subtraction. So minus the log base 5 of z. Then we're going to have to take our exponents down as coefficients using the property of logarithm of a power here. So this is going to be 2 log base 5 of x plus 3 log base 5 of y minus log base 5 of z. All right, and then the last one, we're going to start off in a similar way. We're going to start with log base 3 of 3. That's 3 times x squared, and so I'm going to separate that multiplication into addition, plus log base 3 of x squared, then the division into the subtraction, minus log base 3 of y to the third, and our powers are dropping down in front of their logarithms. One more thing to do here, though, is log base 3 of 3 is known because that's all numbers. There's no letter inside of that one, and I know what log base 3 of 3 is. What power of 3 is 3? 3 is the first power of 3, so we're going to simplify that to 1. Just evaluate log base 3 of 3. It's 1 plus, and then when our power 2 comes down here, we'll have that 2 times the log base 3 of x minus, and our 3 power drops down, times the log base 3 of y. So 1 plus 2 log base 3 of x minus 3 log base 3 of y. Okay, so now we're going to do the reverse. We're going to take these expanded and simplify them into a single logarithm. So the first thing to do is pull your powers, if you have them, back up. So this will be log base 3 of 5 squared plus log base 3 of 2 cubed. Now, if you have numbers like 5 squared, go ahead and figure out what 5 squared and 2 cubed are so that we can simplify those numbers before we combine into a single logarithm. So this is log base 3 of 25 plus log base 3 of 8. That finishes the logarithm of a power property. Then we're going to take the addition and condense it to multiplication. This is going to be log base 3 of 25 times 8. And 25 times 8 is 200. So we would finish off with log base 3 of 200. Okay, now let's look at the next one. The next one, again, we're going to take our powers up. So this will give us log of x to the 4th to the half minus log y to the 5th to the half. I'm just taking up the half. I'm not taking up the minus. The minus I can deal with later. I'm going to deal with that as a division later. I don't need to take it up with the power. Okay. Now I can simplify the power on the first one, multiplying those two powers together using exponent rules. We're gonna use our exponent rules from chapter 2 along with our logarithmic rules to get these things simplified. So this is log of x squared, because 4 times a half is 2, minus the log of y to the 5 over 2, multiplying the powers, 5 times a half is 5 over 2. Then we're going to take that subtraction and convert it into a division. So we're going to have the log of x squared over y to the 5 halves. I need some more room on some of these. So in the next one, let's get our powers up. Okay, so this is log base b of 10 to the 3rd minus log base b of 5 to the 4th plus log base b of 3 squared. I don't have tons of room, so I'm going to simplify those over here. This is log base b of 10 to the 3rd is 1,000 minus log base b of 5 to the 4th. I think it's, I forgot 5 to the 4th. I think it's 625. It is 625. 625. And then plus log base b of 3 squared. So that's log base b of 9. Okay. Then we need to do the multiplication and division. I like to do the multiplication first. The two that are positive, I'm going to pull together, and I'll save the one that's negative for later. So this is going to turn into log base b of 1,000 times 9. So that's going to be 9,000 minus log base b of 625. So log base b of, I need to simplify the 9,000 divided by 625 and get a reduced fraction for it. So if I do that, 9,000 divided by 625 is, now the decimal is not too terrible for that. So you could leave the inside as 14.4, or you can make it 72 fifths. I'm going to go with the 72 fifths just because the division turns into a fraction normally, and if I have a fraction, I'm going to keep things in fraction form unless I'm like told to go decimal on it. So log base b of 72 fifths. No way I could have fit that all in that little bitty space there. So, all right. I'll probably go down into this space when I do the next one. So powers come up. We'll keep those powers coming up here as well. So we'll have natural log of 4 to the third minus the quantity, natural log of 5 to the fourth, plus the natural log of 3 squared. Okay, 4 to the third is 64, so natural log of 64 minus natural log of 5 to the fourth, which should be 625 again, parentheses there, and then the natural log of 9. This time, these two are going to combine in the parentheses there. So natural log of 64 minus natural log, I'm going to have to multiply those together. So I'll have 625 times 9 is 5,625. And then we're going to pull division on that. And so this is going to be the natural log of 64 on top, because that's the positive one, over 5,625 on bottom, because that's the negative one. And only that one reduces. So we'll be done. If it did reduce, I would, of course, reduce it. But I don't believe that it does. Okay. So lots there with our properties of logarithms, especially in some of these that are using all three properties together. When we're condensing, pull our powers first, then do the add, subtracts into multiply, divide. When we are expanding, it's the reverse. Separate your multiplication and division into add, subtract first, then pull your powers down as coefficients. Okay. Change the base formula. Again, this thing's a little bitty thing at the end. They wanted us to check something by graphing to show that two things are the same. But I guess they're looking at, oops, too many pages. They're looking at checking that, there it is. I was looking for the two functions they were graphing. They want us to check that y equals log base 2 of x is equivalent to y equals log of x over log of 2. Let's check those two things. Okay, y equals log base 2 of x, and y equals log of x divided by log of 2. So we should be able to see that the two graphs are identical, or really just one function. They're the same thing. You can see the dotted line shows up right on the solid, and they are the same. So what we've done is taken one function as a base of 2 and changed into two different logarithms with a different base. These are both base 10. Sometimes it's nice because you might be able to evaluate part of it with a different base that you can't evaluate with a regular base. But for the most part, it's simpler to leave it with a base of 2 than to get two logarithms with a different base. So we don't do this a ton. But it could make something nicer in like a very specific case. So it's one more property. It's just not used very often. But while we're talking about properties, we're going to throw this one in and have all of our properties together. Okay, so write y equals log base 6 of x in an equivalent expression using base 10. So this would be y equals log of x over log of 6. So I take the logarithm of the argument divided by the logarithm of the base. That's what you can see down here in this formula as well. The log base b of x is the same thing as the log base a of x over the log base a of b. So the base is the new thing that you're dividing by. It does not have to be 10. It could be e or anything else. So use the results to graph. I guess I can graph these both. Okay, so change my base to 6 and change this to 6. Ta-da! Your two functions are the same again. So we use the results to graph them and confirm they're the same. What's the domain? Well, it's a logarithm, so its domain is 0 to infinity. What is its x-intercept? It's a logarithm. So it's 1, 0. We should have noticed that was the x-intercept when we did these back in 3, 9 also. Unless there was an a value added on to my logarithmic function, that's not going to move. In this case, I don't have one added on, but in the regressions, I'll have an a value added on that will move the x-intercepts. Okay. Last little bit with our change of base formula. Use change of base to determine the log base 4 of 1024. Okay, so using base 10, this would be the log of 1024 divided by the log of 4, or using base e, this would be the natural log of 1024 divided by the natural log of 4. Okay? And that's just a number, so we're just going to evaluate it. If we evaluate the log base 4 of 1024, click, it's 5. And if I do the log of 1024, that's not 5. But then when I divide it by the log of 4, oops, I meant to hit divide. I'm going to say enter. Divided by the log of 4, ooh, I got 5. And if I do the natural log of 1024, that's not 5. But when I divide it by the natural log of 4, ooh, it's 5. So they're all the same. All give approximately, oh, not approximately, equal to 5. All give 5. So just again, showing the equivalency that you can do things silly ways and get the same answer. It's often not efficient, but occasionally this one comes up. Sometimes mostly in programming where computers deal better in base E or base 10.